Check one, two, three. 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 Check one, two, three.
Good evening, everybody. Uh, Start in about 2-3 minutes time. If I'm completely audible, please put a thumbs up in the chat, or you can send a message. One person has sent it. Maybe about two more people can send it. It'll be great. Okay, great. Welcome everybody for another session of helpline. So we were discussing our unit exam paper. We have finished discussing, I think, 3 questions. We can continue discussion from there. Question number 4. Question number 4. So unit discussion, question number 4, right? Have a look. Question number 4. Total mass of a train with the locomotive is 4 × 10⁵ kilogram. Total mass 4 × 10⁵ kilogram. Due to the force exerted by the locomotive, the train accelerates on the horizontal path from rest to a velocity 54 kilometers per hour. So here you go. Here you have a train. From rest, there is an acceleration up to 54 kilometers per hour. You can convert, sir. You can convert that. Time taken 5 minutes. 5 minutes, 300 seconds. 300 seconds. Frictional resistive force on the train is 40 newtons per kilograms. If I mark it here, 40 newtons per kilogram per 1000 kilogram. This you have to multiply by 400. By 400 10⁻³ kilogram. So 400 times. Air resistance is directly proportional to the square of the velocity of the train. So air resistance is also there. Directly proportional to the square of the velocity. So air resistance directly proportional to the square of the velocity. They're telling you when the velocity is 18 kilometer per hour, air resistance is going to be 500 Newton. These are the data given. Data given. Right. Find the velocity of the train after 5 minutes. Find the velocity of the train after 5 minutes in meters per second. Meters per second. So 5 minutes here. The conversion 36 kilometer per hour is 10 meters per second. 1 kilometer per hour is 10/36 meters per second. 54 kilometers per hour will be 10/36 multiplied by 54. 10/36 multiplied by 54, you'll get your answer 15 meters per second. There you go, 15 meters per second. Roman 1. Roman 2. Roman 2. Find the distance moved by the train with an acceleration. Find the distance moved by the train with an acceleration. Now be careful, okay? Here, from rest to this velocity, there's going to be acceleration. What are they asking you? Find the distance moved by the train with an acceleration. Yeah, with an acceleration. Now look at this carefully. If you read the question very carefully here, total mass of the train is given 4 × 10⁵. Due to force exerted by the locomotive, train accelerates on the linear horizontal path from rest to 54 in 5 minutes. Frictional resistive force acting is 40 × 10⁻³. Air resistive forces on the train is directly proportional to the square of the velocity. Air resistance is 500 newtons when the velocity of the train is 18 kilometer per hour. 18 kilometer per hour. Right. Now, distance moved by the train during acceleration. So here you go. Initial velocity 0. 15 divided by 2 multiplied by 300. So around 225 meters. Around 225 meters. Right. Next one. Find the work done by the resistive frictional force during that time. Work done by the resistive frictional force during that time. Okay. Work done by the resistive frictional force during that time. Have a look. Work done by resistive frictional force. Resistive frictional force. So 40 times 400, 225 meters. To get your answer, 3.6, 10 to the power 6 joules. Roman 4. Find the air resistive force when the velocity is 54 km per hour. Look below. Air resistance proportional to velocity squared. I hope you understood this. Air resistance is K times V squared. They are giving you air resistance here 500 Newton. K times 18 kilometers per hour. 18 kilometers per hour. So I hope you remember this. 36 kilometer per hour is 10 meter per second. 18 kilometer per hour is actually 5 meters per second. Pi squared. K is equal to 500 divided by 25. Your answer is going to be 20 Newton meter squared if you write it. S squared m minus 2. Right. K is 20. Now they're asking you, find the air resistive force. Air resistive force is kV squared. V squared is 15 squared. 20 multiplied by 225. How much? 450. 4,500 newtons. So there you go, 4,500 newtons. Roman 5. Roman 5. Consider that the average air resistive force acting on the train during the first 5 minutes is 20% of the value at that of 54 km per hour. So average air resistive force. Average is going to be 20% of 4,500, 2 zeros, 900 newtons, right? Work done by air resistive force. Work done by air resistive force. Force into distance travel, 225 is the distance. 900 multiplied by 225, 202, 500 joules. 202, 500 joules, okay, no? 202, 500 joules. Find the increment of kinetic energy during this time. Increase in kinetic energy. Increase in kinetic energy. Final kinetic energy. I given you the mass, no? 4 10 to the power 5, 15 squared minus initial. Simplify this. 4.5 10 to the power 7 joules. 4.5 10 to the power 7 joules. 0.5 10 to the power 7 joules. So you can see the progression. So where did we start? First by converting. Average uniform acceleration is there, we can assume. Now, moment to moment, their resistance will change, but later they are telling you it's going with average. So here, uniform acceleration, starting from rest, final velocity 15, divide by 2 into displacement, time will give you displacement. Here, work done by frictional resistive force, force in displacement you can get. They are giving you at 18 km per hour the air resistive force is 500. So we can find K. Once you find K for any velocity, you can find the air resistive force. Now the air resistance force here is actually average is 20% of this. So air resistance average 20% here, 900. So work done is 900 into 225, 2 lakhs, 2500. Increase in kinetic energy is 4.5. Or final kinetic energy minus initial kinetic energy. From there you will get 4.5 10 to the power 7. So pretty direct in the basic calculation. Right? Hence find the power. So what is the power? Work done by external force. Work done by external force. So let's apply work energy principle. Work done by external force equals increase in kinetic energy plus work done by resistive forces. Increase in kinetic energy already we have marked 4.5 10 to the power 7. Work done by resistive, there are two resistive forces. One is of course frictional resistance 3.6 10 to the power 6 plus work done by air resistance. There you go. Total work done you can find. Total work done 4.88 025 10 to the power 7. So what can you say about the power? Work done by external force divided by time. 4.88025 10 to the power 7. Whole thing divided by 300 seconds. If you divide it, 1.627 10 to the power 5 watt. 1.627 10 to the power 5 watt. There you go. So once you find the total work done by external force, work done by external force divided by time will give you the required power. Will give you the required power. Right. Part B. Part A is finished. Part B of the problem. Part B of the problem. Read. Mass of a train engine is 50 10 to the power 3 kg. Mass of the compartments are 300 10 to the power 3 kg. This train moves up an acceleration along an inclined plane 1:100. That means if I travel 100 meters along the train, along the slope, height changes by 1. Frictional resistive force is 50 newtons per 1000. It has reached a velocity 36 kilometer per hour after moving 1 kilometer along the plane. Right. So what can you say? So here you go. Train is there. Two compartments are drawn in the picture. So mass of the train 50 10 to the power 3 g. Two components or compartments. I'll advance draw it. 600 10 to the power 3 g. 10 to the power 3 g. Are compartments. Okay, plural form given. So these three are. Both are 300. Huh? Both are 300. Right. Take components along the plane. Very important. First sign. So if you take the sign components, down the plane, So 300 10 to the power 3 g sine theta 50 10 to the power 3 sine theta. There will be engine force separate. Resistive force is 50 Newton per 1000. That's separately. Yeah? This component of weight, that is separately. 50 Newton every 1000, 50 times 50, 2500. Here 50 Newton every 1000, 50 times 300. 5 times 300, 1005, 15,000. So 15,000 Newtons acting downwards from both sides. Apart from the weight. Apart from the weight. Right. Part A. Increment of the gravitational potential energy. Increment of the gravitational potential energy is mgh. Total mass is going to be 350. 350 10 to the power 3 g. What can you say about the height? What can you say about the height? So if you go 1000 meters, this is going to be 1000 sine theta, right? So h is going to be 1000 sine theta. 350 10 to the power 3 g is 10. 1000 sine theta is already given. Opposite over hypotenuse. They have told you, if I travel 100, the height changes by 1. Sine theta is 1 over 100. Simplify this carefully, 2 zeros, 2 zeros. 3.5, 10 to the power 4, 10 to the power 5, 10 to the power 7 joules. 3.5, 10 to the power 7 joules. 3.5, 10 to the power 7 joules. Okay, now? Part B. Work done against frictional resistive force. Frictional resistive force is non-conservative. Work done by frictional resistive force. Frictional resistive force is work done by friction. Total work done by friction 15,000 plus 2,500. 17,500 multiplied by 1000. How much? 1.75 10 to the power 7 joules. 1.75 10 to the power 7 joules. Next is increment of kinetic energy after moving 1000 meters. Part C I'll do here. Final kinetic energy minus initial kinetic energy. Final minus initial. Final kinetic energy half. Total mass 350 10 to the power 3 into velocity squared. Velocity is 36. Is it starting from rest? Yeah. So assume it at rest 10 square. 175 10 to the power 5 or 1.75 10 to the power 7 joules. 1.75 10 to the power 7 joules. Okay. Power of the engine. Simple work. So increase in gravitational potential energy found. Work done by friction found. Increase in energy found. Yeah. Increase in energy found. Then what do you do? Work done by the engine or external force. Increase in kinetic energy plus work done by resistive. Increase in kinetic energy That is, of course, we have already found 1.75 10 to the power 7 plus. Work done by friction 17,500 multiplied by 1000 plus. Component of weight 350 10 to the power 3 g sine theta multiplied by distance travel 1000. Turn back and look. 350 350 10 to the power 3 g. What is this 1000 sine theta? 1000 sine theta is going to be the height. So carefully 1.75 10 to the power 7. This part is also 1.75 10 to the power 7. This part here 350 10 to the power 3. We have done it. 3.5 10 to the power 7. 3.5 10 to the power 7. Okay, no? Simplify this. 1.75, 1.75, 3.5, 3.5, 3.5, 7. 10 to the power 7 joules. Power developed by the engine. Power developed by the engine is work done by the engine divided by time. Work done by the engine 7 10 to the power 7. All this work done divided by time taken, they are giving you. Now time taken you have to find, otherwise you can't find the power. No? Time taken you must find. Huh? How will you find the time taken? You can do a calculation here. S equals U plus V divided by 2 into T. 1000 meters up the plane starting from rest 10 over 2 T. 2000 divided by that means 200 seconds. Substitute 200 seconds. 3.5 10 to the power 5 watt. 0.5 10 to the power 5 watt. 3.5 10 to the power 5 watt. So it's easy work. All you do is apply energy carefully. If you apply energy carefully, directly the answers will come. You can see, you know, in the calculation, it's very simple. Now, once you reach here, you know, I had to find the time. So you find the time. Displacement 1000, starting from rest, velocity 10, divide by 2 into T. Simplify 200 seconds. 200 seconds, you can use it to find the power. Okay, no? So this is going to be your part D. Part E. Force exerted on the compartment by the engine. Now here you can mark the tension. Is tension. Force exerted on the compartment by the engine. That means they are finding the tension in the cable. Tension in the cable. Right. That's going to be part E. Let's find the acceleration. Starting from rest. Time taken 200 seconds. Acceleration 1 over 20. Acceleration 1 over 20. Then what else? Apply F equal ma for the compartment. Who is pulling the compartment? Tension. What is acting downwards? Component of weight. 300 10 to the power 3 g sine theta. Apart from that, you have resistive forces acting. Resistive forces here 15,000. 15,000. Mass into acceleration. Mass is 300 10 to the power 3. Acceleration 1 over 20. Tension equal 300 10 to the power 3 g sine theta is 1 over 100 plus 15,000 plus 300 10 to the power 3 into 1 over 20. Simplify this. Tension can be found. Tension in the cable can be found. Tension in the cable 60,000 newtons. 60,000 newtons. There you go. You can simply calculate 2020 here, 30,000 there, 15,000, 45,000. 45,000, 0, 0, 15, 15,000. 45,000, 15,000, 60,000. Tension in the cable by the engine 60,000 newtons. 60,000 newtons. Okay, now. So there you go. Question number 4. Question number 4 completely done. Okay, question number 4 completely done. Now we come to a final question. Question number 5. Question number 5. Mass train engine is state work energy principle. So you must write it. Work done, write in words. I'm quickly writing here. Work done by external force equals increase in kinetic energy, or write in words, not like this. Increase in kinetic energy plus work done by resistive forces. Work done by resistive forces. Okay. When a bullet colliding perpendicular to a stationary block has penetrated a distance 2 centimeter and 1/5 of its initial velocity is lost. Find the distance traveled by the bullet in the block when it comes to rest. Consider resistive forces acting on the bullet to be constant. So you can apply here. Just before the bullet enters, let's say velocity is u. After traveling 2 centimeter, 1/5 is lost. So 4/5 u is there. Find the distance traveled by the bullet in the block before it comes to rest. So what's happening here is only resistive force is acting. Only resistive force is acting. So work done by external force, no external force. Increase in kinetic energy plus work done by resistive forces. You write in words in the exam, not like this. Write in words. Work done by external force. There is no external work done. Loss in kinetic energy, final kinetic energy minus initial, half mu squared. Work done by resistive force. Friction into total distance traveled x. F into x is half mu squared equation 1. For this bit also you will write. Work done by external force equals increase in kinetic energy, half m 4u squared over 5 minus initial half mu squared. Work done by resistive force 2 centimeter. Half mu squared, half m 16u squared over 25, f times 2. Half mu squared, 16 over 25, f times 2, equation number 2. Second equation divide by the first equation. Sorry, first equation divide by the second, easier. First equation divide by the second. First equation f times x, f times 2. Half mu squared, 25 minus 16 divided by 25. Simplify half mu squared ff x equals 2 times 25 divided by 9. 50 over 9 centimeters. 50 over 9 centimeters. 50 over 9 centimeters. There you go. 50 over 9 centimeters. Right? 50 over 9 centimeters. Part C. A child of mass 25 kilograms sliding from A to B with a speed 4 meters per seesaw, mass slide. Calculate the work done to overcome friction. Calculate the work done to overcome friction. Part C. Here height is 0.5 meters. Here height is 4 meters. Child is coming from rest. Leaves here with a speed 4 meters per second. Let me name this as A, name this as B. This is GP equals 0. Remember, in your picture, the diagram should be correct. Huh? Whatever you are marking. So work done by friction. Total energy at A, gravitational potential energy plus kinetic energy at A. Gravitational potential energy was the mass of the child, 25. 25 GH. 250 times 4,000 joules. No kinetic energy. Total energy at B. Gravitational potential energy at B plus kinetic energy at B. Gravitational potential energy at B is going to be 25 G into H. Kinetic energy half 25 4 square. Simplify this carefully. 25 times 5. 16 divided by 2, 8. 8 times 25, 200. 125 plus 200, 325. Interesting. What happened to the rest? Lost. Work done against friction. Work done against friction. That's 1000 minus 325. 675 joules. 675 joules. 675 joules. Okay, no? 675 joules. Part D. So these are easy work. Energy here, energy here. Difference is the work done against friction. Very easy to find. Part D. A car moving along a horizontal road increases its velocity by 20 meters per second from rest. So here part D, car is there at rest. Increases the velocity up to how much? 20 meters per second. 20 meters per second, moving 100 meters. Moving 100 meters. Mass of the car is 200 kilogram. Constant resistive force 200 Newton is acting. Find the work done by the engine. Directly apply work done by increase in kinetic energy plus work done by resistive force. Work done by the engine increase is half mass into 20 squared, initially 0. Work done by resistive is 200 multiplied by 100. So 400 here, 2 zeros plus. How much altogether? 60,000 joules. Work done. Part B. Part B. Right. State law of conservation of linear momentum. What's linear momentum? When there is no external force acting on the system, total linear momentum is conserved. That you must write. When there is no force acting on the system, the total linear momentum is conserved. Next, they're asking state law of conservation of energy. How do you state that? Total energy cannot be created or destroyed. It can be converted from one form to another. Energy cannot be created or destroyed. It can be converted from one form to another. Okay, right. So capital B, part A done, part B. Part B. Right. Look at this. End of a smooth curved path PQ. End of a smooth curved path PQ. This is smooth. Is connected to a rough horizontal plane. Rough horizontal plane. Mass B is at rest. Mass B is at rest at Q. Mass P is released from rest. Mass A is released from rest. So this is released from rest. It will travel and collide with B. Right. Two masses move along the horizontal surface and fall to the ground at positions A dash and B dash. Okay. B dash will fall there. A dash will fall closer. Right. This is 1.6 meter where B dash is falling. This is 0.8 meter where A dash is falling. Here you have a distance of 2 meters. 2 meters to travel. There you go. Right. And here the height is 0.8 meters. Okay. This height we don't know. This height we don't know. Right. Now look. Coefficient of kinetic friction between the cement block and B is 0.5. And that of A is 2140. So friction forces are different as well. Find the velocity in which B leaves point R. Find the velocity in which A leaves R. That from here. We know the distances. We can find. We know the distances. That's fine. So I'll do for B first. B travels height 0.8. Velocity that B travels. BB. Okay. Velocity that A travels. BA. Right. Part B, Roman 1. S equal ut plus half a t squared vertically downwards. 0.8 is for B. Yeah? No vertical velocity half 10t squared. T squared is 1.6 divided by 10. That's 0.16. Time is going to be square root 0.16. That's going to be 0.4 seconds. Then what do you do? Horizontal range. S equal ut plus half at squared forward on B. 1.6 meter velocity at B, time taken 0.4 seconds. No horizontal acceleration, projectile motion. VB is equal to 4 meters per second when it's leaving R. Roman 2. S equal ut plus, time will be the same, no, same height. Time will be the same. Apply this for A. 0.8 meters, velocity of A, time taken is the same. Time taken will be 0.4. Velocity at A is 2 meter per second. At a small sentence. The height that A falls and the height that B falls is the same. The height that A falls and the height that B falls is the same. The height falling is the same. Therefore, the time taken will also be the same. Therefore, the time taken will also be the same. Time taken will also be the same. Right. See Roman 1. What is the velocity of B just after the collision? Now, just before leaving here, velocity is 4. B just after the collision. BB dash. Friction is there. Huh? Friction. Kinetic friction is there. That's going to be mu K times normal reaction. Mass of B is 1.5, 15 Newton. Mu K is going to be 0.5. So 0.5 times 15, that's going to be 7.5 Newton friction. Distance there is 2 meters. So just before collision, let's apply work energy principle. Work done by external force equals increase in kinetic energy plus work done by resistive forces. Work done by external force is 0. Increase in kinetic energy, final kinetic energy. Final kinetic energy. Half mass into force squared. Half mass into VB dash. Work done by resistive force. 7.5 into 2 meters. Take it that side. Half mass 1.5. VB dash squared minus 16. 15. Jump a decimal. 10. 20. BB dash squared is 36. BB dash is going to be square root 36. How much? 6 meter per second. 6 meter per second. Simple work. Roman 2. What's the velocity of A just after the collision? Same theory, but different mass. Same theory, but different mass. VA dash. Moving out 2 meters per second. Distance travel 2 meters. Friction force. Friction force 21 over 40 multiplied by 10. 21 divided by 40 multiplied by 10. That's 21 over 40 multiplied by normal reaction 10. How much? 5.25 newtons. 5.25 newtons. 5.25 newtons. Work done by external force equals increase in kinetic energy plus work done by resistive forces. No external work done, increase in kinetic energies. Half mass of B 2 squared. Half mass of B VA dash squared. Work done by resistive force 5.25 multiplied by 2 meters. Simplify this. half mass VA squared minus 4. 5.25 times 2, how much? 10.5. Mass is 1. VA dash squared minus 4, 21. VA dash squared is 25. VA dash is going to be 5. Velocity is found. Velocity is found. So C Roman 1, C Roman 2 found. What is the velocity of A just before collision? Hence find the height h. Now what? Velocity leaving the table found. Velocity just before the just after the collision found. Just after the collision found. I'm working backwards. Now after the collision only it's going. No. So after the collision we have found initially. After the collision, no, it's going. After the collision, we have found the velocity. Now what? Apply for the collision. Apply for the collision, part D. So B is at rest. A is coming with velocity VA. Then after collision, A will travel with VA dash. B will travel with BB dash. Finished. Apply. Total initial linear momentum. Please write in words, full words. Total initial linear momentum of the system. Total final linear momentum of the system. Initial linear momentum mass MA 1 times VA. 1.5 times 0 at rest. After collision, 1 times here 5. Please put the direction. Next is 1.5 times, it's going with 6. No? B is going with 6, if I'm not mistaken. Just after the collision, B is 6, 5. Simplified VA, 5 plus 9, 14 meters per second. 14 meters per second. So if we go back to the picture, just before the collision here, 14 meters per second. They're asking the height here. Let me take this as the GP equals 0 line. This is position X. This is position Y. Let me apply energy. Let me apply energy. Total energy at X equals total energy at Y. Gravitational potential energy mg capital H half mv 14 square. Cancel off. 10h 196 divided by 2. H is equal to 9, 8 divided by 10, 9.8 meters. So 9.8 meters found. Part E is the collision elastic. Total kinetic energy before the collision. Total kinetic energy before collision. Only A is traveling, no? Half mass into 14 squared. 196 divided by 2, that's going to be 98 joules. Total kinetic energy after collision. After collision, 2 particles are traveling. Half 1 into 5 squared. Half 1.5 into 6 squared. Here, be careful. Here, 5 squared. 25 divided by 2 is 12.5. 36. 36 divided by 2 is going to be 18. 18 times 15. 27. From this you have 39.5 joules. Initial kinetic energy 98, final kinetic energy 35. What can you say? It is an inelastic collision. There is a kinetic energy loss. There is a kinetic energy loss. Therefore, it is inelastic. It is inelastic. Finish. Easy. Technically easy work. Huh? So you're applying law of conservation of linear momentum. After you apply law of conservation of linear momentum, you know the velocity. Then go back to your picture. Go back to your picture. Here velocity 14 just before collision. That means for this part I can apply energy because smooth. Smooth. Smooth I can apply, no? Then what we can do is we can get your required answers. Okay. Right. Part C. Part C. A large windmill is built to produce electricity and surface area cut by the wings are 1400. So this surface area 1400 meters square, right? Velocity of the wind incident on it. Velocity of the wind incident on it 15 meters per second. Find the mass flow rate. Mass flow rate. All no. AV rho. 1400 15 into density 1.2. How much? Mass flow rate can be easily found. Mass flow rate can be easily found. 25,200 kilograms per second. Right. Part A. Part B. Velocity of the wind reduces from to 30 after collision. And the wind does not change direction. Find the rate of decrement of kinetic energy. Rate of loss of kinetic energy. That's initial kinetic energy minus final kinetic energy divided by time. Half common m over t common 15 squared minus 13 squared. M over t is mass flow rate found. 25,200. 15 minus 13 is 2. 15 plus 13 is going to be what? 28. Multiply it. 705 600 watt. Rate of loss of kinetic energy. Rate of loss of kinetic energy. Part C. Efficiency of this wind turbine is 70%. How many such wind turbines are needed to get an output of 1000 megawatt? So efficiency, part C, efficiency is power output over power input multiplied by 100. Power output we don't know, but the power input we know. 705, 600 into 100. Therefore, power output you can find 705, 70%, 493, 920 watt. How out? Number of turbines. Number of turbines will be 1000 megawatt. Mega convert to watt divided by 493, 920 watt. How many turbines? To divide, you can find it. 2025 turbines. 2025 turbines. 2025 turbines. Easy, no? From the output, required output divided by output of one turbine will give you number of turbines. Write two advantages and two disadvantages of generating electricity from wind. Advantages. It's a renewable source. Number two, less carbon emission. Number three, in terms of what you call advantages, it's more like a disadvantage. So two advantages there: renewable source, less carbon dioxide emissions. Disadvantages: the wind speed won't be uniform throughout the year. Number one, wind speed won't be uniform. Number two, to generate, we need a lot of power mills. There'll be a problem with space right there. We need more space. Disadvantages: we need more space. Since the wind is not uniform throughout the year, since the wind is not uniform throughout the year, since the wind is not uniform throughout the year, it is difficult to produce. It is difficult to produce a constant uniform output continuously. Constant uniform output continuously. Okay, right, there you go. We have discussed the MCQs and the essay questions of your unit test number 4. So hopefully you can look at this and you can correct your mistakes and face your next exams well. Okay. Keep working, keep studying, always believe in the process, because guaranteed you're getting better. Guaranteed you're getting better. Okay. See you next time.